4, 3, 2, cue. Music up.
Hello. Today we are going to have a report on the nature of electricity. Our guest reporters will be Mark, Patty, Tom, and of course myself, Lisa. As we all know, electricity is one of the most important things in our lives. We use it in our homes, it is stored in batteries in our cars, it lights our streets, runs our factories, and we can even have fun with it. Electricity is all around us all the time. Even when the power goes off, leaving us in the dark. I bet you never knew you could find electricity in trees, stones, in the air, the ocean. Electricity is even inside each one of us. So let's talk about what electricity does for us and what it is. Electricity. What is it? What makes it work?
Well, we know that electricity is caused by the presence or movement of electrons. They are the tiny parts whirling around the nucleus of the atom. Atoms are the smallest bits of matter that make up everything we know about. They are so small, it's kind of hard to imagine. There are millions of atoms in this little drop of water. So you see, atoms are very small, and of course, electrons are even smaller. There are about 100 different kinds of atoms. Each of them has a nucleus and electrons. In every nucleus, we find protons and neutrons. The protons are plus charge, while the neutrons have no charge. The electrons have a minus charge. Normally, atoms contain the same number of electrons and protons. This way, the plus and minus charges are equal, or we say electrically balanced. Sometimes, though, electrons can be pushed off or pulled away from the atoms, or free electrons can be added to the atoms. In either way, this will upset the balance or equilibrium. The atoms don't like this situation, though, and they will try to reestablish equilibrium. This usually happens very fast, and when it does, we have an electrical discharge. This is the type of electricity that is hard to control. We call it static electricity. Here's a way we can detect the presence of an electric charge. This is called an electroscope. See the balls? They are close together, but not touching. Rubbing this glass rod with a silk cloth will pull electrons off the cloth and onto the glass. This glass rod with its extra electrons is now minus charged. Now I'll transfer the electrons to the balls. Now the rod and the balls all have the same charge. See how they repel one another? Now I'll remove the charge by touching the balls with my finger. This time, let's set up opposite charges. Rubbing the glass again, I'm building up electrons. We're making a minus charge here, so I'll transfer the minus charge to just one ball. We can get a plus charge by rubbing a rubber comb on a piece of wool. When we touch the comb to this other ball, it will pull off electrons from the ball to the comb. Now the ball has a plus charge, so they come together, touch, and then go apart again. From these two demonstrations, we can say that like charges repel, while opposite charges attract each other. The Earth is a giant storehouse of electricity. It can take on or give off enough electrons to neutralize the charge on any object. This is one reason why we have lightning. Lightning is a giant electric discharge. It can happen between the clouds and the Earth, or just between the clouds. Differences build up between these places in their potentials. That's what we call the difference between their charges. When the difference in potential is great enough, there is a great flash. The flash disturbs the air, so there is a loud crack, and we call that thunder. This static electricity generator shows us how we can use energy to pull electrons off of the atoms and build up a static charge until it discharges. So there you are, Lisa.
Thanks, Mark. Now, Patty, would you tell us about current?
Okay, Lisa. Current. An electric current is a stream of moving charges. When an electric current travels through a wire, like this one, it flows, sort of like a stream. A stream flows downhill because gravity pulls the water. Electricity flows as long as there are differences in the levels of electrical charge. If we want to make electricity useful, we have to keep the current flowing. We have to keep the electrons from reaching equilibrium. Here's one way, using a battery. This battery stores electricity. In this way, we can have electricity whenever and wherever we need it. As you can see, this battery has two terminals, one plus and one minus. There are chemicals in this battery that provide a source of electrons for a current. This current will flow when we attach a wire from one terminal to the other. The electrons will flow from the negative terminal to the positive terminal. When there is a loop like this one, we call it a circuit. It's a good idea not to leave the wires attached to the battery because it will burn the battery out. This wire is made of copper, covered with plastic. As we explained before, the atoms are giving up and taking on electrons to create this flow. They flow very easily through copper. Copper conducts well. Everything conducts electricity. Some materials do it well, others do it poorly. There can be great differences between the two extremes. Here's a way we can measure how well things conduct electricity. First, we need a battery, like this dry cell. Then we need some wire and a meter like this one. This meter shows us when there's a current in the wire. Let's see if this meter can show us how well different things conduct. You can do this experiment with the materials you want to test. I have a few things here. So let's try each one. The penny completes this circuit and registers a 10 on the meter, so copper conducts. Now let's try this leaf. Okay, this leaf conducts too. It registers 1 on the meter. This piece of wood doesn't conduct so well. It registers 0 on the meter. Let's see what happens when we wet this wood. Now our meter shows 4. Water can help this wood conduct, but as you can see, still not as well as the copper. Finally, let's try this piece of plastic. Plastic doesn't conduct well enough to register. It insulates. Materials that don't conduct well are called insulators. Let's see what happens when we wet the plastic. It's still a good insulator. This is the reason wires are covered with plastic or rubber. This insulation will keep most electrons from escaping the wire. These big power lines use insulators to keep the electricity from flowing into the ground. Those big insulators are ceramic. Ceramics and glass are not good conductors. If there were bare wires in your home, you could get a very bad shock. You should be very careful whenever you have anything to do with electricity, even changing a light bulb. Now here's another way we can make a poor conductor work for us. A toaster. It has many metal coils inside that heat up. A toaster heats up because these coils are most commonly made of nichrome. Nichrome conducts electricity, but not as well as most metals, so it is hard for the electrons to move. They must work so hard that heat is given off. This is also how an electric stove works, or any electric thing that gives off heat. A light bulb gives off heat and light. This is because the little filament inside the bulb does not conduct easily. The filament heats up until it is glowing hot, and it gives off light. It does not burn out because there is no oxygen in the bulb. All the air has been pumped out of the bulb. Lisa?
Thank you, Patty. And finally, we'll talk about some unusual things that electricity does. Tom?
Many years ago, a man named Ørsted discovered a relationship between electricity and the phenomenon called magnetism. He had been experimenting with a battery. He discovered that holding an electrical wire near a compass would make the needle move. Reversing the wires will reverse the direction the current flows, and the compass moves in the opposite direction. Another man, Ampere, figured that coiling this wire would let more wire near this compass, so the force would be stronger. What happens when the current flows is that this bar acts just like a magnet. This is called an electromagnet. When the current is turned off, the bar loses its magnetic properties. An electric motor works in a similar way. You see, here's a large electromagnet around the outside. Inside there is another electromagnet that can spin around. This electromagnet will turn around and around when the current is turned on. We can show this with two magnets. This one magnet is mounted so it can turn around freely. As you remember with plus and minus particles, opposites attract, likes repel. It's the same with magnets. If I hold the minus side of this magnet and put it next to the minus side of this magnet, it tries to get away. Now, if I keep it up like this, I can keep this magnet moving pretty well. This is what happens inside of a motor. But instead of using regular magnets, we use electromagnets. We can find electric motors just about everywhere we look. Some of them are tiny, in this clock, in your record player, or larger ones, in this fan, or really big ones like in the factory. Have you ever wondered how electricity was made or where it comes from? We use a lot of electricity every day, and it takes a lot of energy to make enough electricity. Electricity is made by large generators. These generators operate using magnetism again. Let me show you. Here's a wire attached to a voltage meter. I'll pass a magnet across the wire like this. The meter shows us that there is a current in the wire, but when I stop, there is no current. Now notice what happens when I pass a magnet faster and faster across the wire. The more energy I use, the greater the power. This is the way a generator works on a small scale. Here's another small generator. When I turn this crank around, these magnets will induce a current in this wire, and the electricity flows. The generators that produce our power are a lot larger, and they turn very, very fast, producing lots of power. Some power stations use moving water to turn the electromagnet, like this. Other power stations heat up water to make steam, and the steam power turns the electromagnet. That electricity is carried to our homes in large cables that conduct very well.
Thanks, Tom. And now you know a little more about electricity. It's all around us, whether we use it to make our lights glow, watch TV, cook our meals. It's in the atoms and all the things around us. And it's even in the atoms in our own bodies. Electricity surrounds us all the time. Remember, electricity is caused by the presence or movement of these electrons. They may be tiny, but they sure pack a large charge. So there you are. And that's all for our electricity report. So for our reporters and myself, thank you and goodbye.